So there's one topic I wanted to mention already yesterday, but I was too slow as usual, and this is topological realizations. So there are sort of two versions of this. Right, maybe I should do this first. Are there any questions regarding what I explained or tried to explain yesterday? Okay, doesn't seem to be the case. So, a topological realization, there's one version which will be defined on the A1 homotopy category for the complex numbers. And the construction is as follows. There is a functor from smooth complex varieties to topological spaces, which takes complex variety and associates to it the analytic space. So you take the complex points in here and then use the analytic topology. This gives a particularly nice topological space. And this construction can be extended. So here we have the Yoneda embedding to all spaces over C. So if you have a space over C, so this is a presheaf on this category with values in simple sets, it can be written as a co-limit over all maps from the standard n simplex times a smooth scheme X going to A. So you just write these sort of representable space over C here. Right. And the functor going this way takes this A and sends it to the complex Betti realization of A, which is then defined using this co-limit. And here you write down the following topological space. You take the associated topological n simplex and take the product with this analytic space. So this is an explicit form of saying, okay, you have this functor and you have the Yoneda embedding, and then you proceed via left-Kahn extension. So in particular, this functor here will be a left adjoint, and then there are some properties which are relatively easy to check. Yeah, maybe I'll write this down first. This has a right adjoint, and it is compatible with products. This you can see from the corresponding property for this construction here. And in particular, if you take the sort of one of the basic weak equivalences, yeah. So this is the product of x with the affine line and then the projection down to x. So under this complex realization, this is just the same as the analytic space of x, product with, and now I have a notational problem, because what I would like to do is I would like to write down the complex numbers, but I wrote down the complex numbers here already, so I have to do something different, right? So let me just write here the analytic topology. going here. And this here is a contractible topological space. So this here is a homotopy equivalence. And one can do a similar check for these Misnevich squares. So if you have a Misnevich distinguished square, the complex realization is obtained by taking analytic spaces here, and then this étale map will become a local homeomorphism, and then you can check that also the sort of the gluing condition, which defines the weak equivalences to some part, this is also preserved under this complex realization. So this here is a push out in top. So we can or we obtain an induced functor on the homotopy categories. So I didn't mention this explicitly when I quickly introduced this basic functoriality yesterday that Frederick referred to already. Of course, if one wants to discuss this functor on the homotopy category, so here we have the usual homotopy category of topological spaces where the weak equivalences are the maps inducing isomorphisms on all homotopy groups, not the genuine homotopy equivalences. So instead of writing this functor, I should say we consider the total left derived of this functor. But usually I will ignore this in the notation. I'd just like to give one example. If one wants to compute the Thom space of a vector bundle of complex varieties, over a complex variety, then this was defined as a quotient of the complement of the zero section. So you have this open inclusion, and when you take associated analytic spaces, then this here is also an open inclusion, and then usually the quotient will not be Hausdorff, will not be a nice topological space. Yeah, but if you consider the left derived, this allows you to replace this co-limit construction suitably, and one construction which works nicely is the one I mentioned. You can take the closed embedding of the projectivization of V into the projectivization of V plus a trivial line bundle. So if you take analytic spaces here, then this here is a closed inclusion of CW complexes. And in particular, it is homotopically well behaved. So from this, we can then see that this is actually the Thom space of the associated complex vector bundle of analytic spaces.
Oliver, but if V, for example, is a CW complex, its realization is a CW complex.
Yeah.
Will it be, can we remove L, the left derived then?
Yes. Yeah.
So the only problem is whether your V and X are CW complexes after realization.
So formally you compute this by making an appropriate cofibrant replacement. And the question is what is meant by cofibrancy here in this context. There is some flexibility in setting up the homotopy theory. But you won't be able to allow open embeddings of all open embeddings of smooth schemes as cofibrations.
Okay.
This will not work. But having all closed embeddings, this will work. And what sort of works basically by definition is to use these projective cofibrations, which are generated by these maps. So there is some flexibility, but not too much.
Okay, but closed embeddings can be cofibrations.
Yeah, you can choose your model structures such that closed embeddings are cofibrations. Okay. Further questions? Then let me discuss a slight variation of this. Another topological realization, which is defined over the real numbers. And there's now a functor going to topological spaces with an action of a group with two elements. Let me write this in a more complicated fashion as the Galois group of the complex numbers over the real numbers. And then you can probably already guess the definition here. So you take something over the real numbers and you extend it to the complex numbers, take the analytic space, and then you have complex conjugation, which gives you the operation, and then this defines a real realization functor from spaces over the real numbers to this category of topological spaces with an involution, and it basically has the same formal properties. Let me just illustrate this with some examples, maybe. Let's see. So the complex realization, and now I take not the real realization, let me take the fixed points under the action. So what do I have? Okay. So the projective line, this would give you CP1, which is homeomorphic to a two-sphere. Here you would get the real projective line, which is homeomorphic to a one-sphere. You can look at the punctured affine line. This would give you the punctured complex plane, which is homotopy equivalent to a one-sphere, and here you would get the punctured real line, which is homotopy equivalent to a zero-sphere. What else do we have? Okay, you can similarly look at punctured affine space. So this would be a 2n-1 sphere. This would be an n-1 sphere. Right, if you have some simplicial set, you can view it as a constant space, and the realization in either case is just the usual topological realization of the simplicial set. And now here's one thing. I had this sort of slightly more interesting example, of a space given by Quillen's K-theory presheaf. And one can also compute its realization. And this is homotopy equivalent to a space which was mentioned yesterday in Matthias' talk. And also in the real case you get O times C. So, yeah?
What if I start from some schemes or the complex numbers and take such x and I take x of c, but I see this as the real negative, as a real manifold?
Yeah.
Which type of realization do I get in this case? I
mean, This here is just, here I really just view this as a topological space, so I don't equip it with any manifold structure. Yeah, so this is just to describe what type of topology you're using. But here it's just a topological space. Yeah. 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 Okay. Okay, I thought the question was, how do you compute this? Yeah, because it's not obvious. Yeah, the construction I gave here was, you take this category of vector bundles, then quilts Q construction, then you take the nerve, then you take a loop space. How do you get this? And the thing is, the way this is defined is, you know what happens on representables. So you would like to express this as a colimit of representables. Of course, we can express anything as a colimit of representables, but this is a huge colimit. So for this, we would need a more reasonable colimit. Let me just state the theorem Röndigs. And yeah, let me stick to the case where the base scheme is regular. It's definitely okay here. There exists weak equivalence from the following space. You take an infinite Grassmannian, and this exists in the category of spaces over S. And let me define this quickly. You have the Grassmannian of rank R, subspaces of some affine space. Yeah. So R linear subspaces of D. And then you can increase the dimension. You can increase it in a very obvious way, increasing D, sort of including an affine space as 0 by a product with 0 in the next one. And you can also increase this here by taking a product with a fixed line, and increasing both these gives you this here. Yeah.
You don't need input A1.
Pardon?
Don't you need input A1?
Oh yeah. When I say this is a weak equivalence, I mean this is an A1 weak equivalence.
A1
Yes, this is in the A1. An A1 weak equivalence. Yeah. And the map can also be described on this space. You have a tautological vector bundle of rank R, and well, by construction of this space here, to give a map from a smooth variety X to K, this is the same as a zero simplex. In this here. So you can specify maps from these spaces by specifying certain classes of bundles in K0. Yeah. And then you take the sort of appropriate map induced on colimits by these tautological bundles. Yeah. And then you have an argument why this here is true. Okay, maybe let me move towards the stable situation, which was already advertised by Frederick. First thing, these category of spaces over S and the A1 homotopy category of S, they both admit pointed versions. So notationally, this is a bit awkward now. I'd like to apologize for that. So you take pre-sheaves with values in pointed simplicial sets. And weak equivalences in here are defined as weak equivalences on underlying unpointed spaces. I always like to make this remark that if you have a smooth variety, there is no guarantee that it actually can be equipped with a base point, because there are varieties over suitable fields without any rational point. Yeah. This is something which topologists don't worry about. They always choose a base point and don't worry about base points. Yeah. Here we have to worry slightly. Okay. This here also has a closed symmetric monoidal structure, and this I have to define. This is the smash product. So if I have two pointed spaces over S, then the smash product is defined as the quotient of the product where you collapse sort of the obvious one-point union. And this gives a closed symmetric monoidal structure. Okay, and here are some examples that we've seen already. Sort of the standard affine cover for the projective line can be rephrased as follows. So here we can choose a base point. It doesn't really matter, but most people then choose infinity, I guess because they like to draw the infinity symbol. So this is then weakly equivalent as pointed spaces to the following. And here the punctured affine line, so affine line minus 0, can be pointed at 1. And just to sort of introduce notation, this here is the simplicial one sphere. So this is a different sphere than this here. I apologize. But, this here has a standard base point. It's here. And this here is usually denoted as GM, the multiplicative group. It's again over the base scheme S. And there's more notation. One can abbreviate. Oh no, this is not an abbreviation. This is a, how do you say, prolongation? This is it's more complicated notation for this sphere. And this is often called a 1-1 sphere. And if you smash these spheres together, you get a 2-1 sphere. So this bigrading convention is supposed to be compatible with the one mentioned by Matthias regarding motivic cohomology. So for the punctured affine plane, you can look at the standard open cover. So you have A1 cross GM, and you have GM cross A1, and they intersect in GM cross GM. And the union is this here. And this is a Nisnevich distinguished square. So what you get here is, if you choose a base point, this is then the same as S1 smash GM, or in this notation, it would be a 3-2 sphere. And just sort of recall, this is the same up to A1 weak equivalence as the group SL2. And more generally, the punctured affine space is then a 2n-1 n-sphere. And if you like, you can compare how these numbers arise with sort of the topological situation. The first number you can read off from the complex points, and then this is more complicated. The sort of the real thing, this is given by the difference of these two numbers. So more generally, whenever you have integers or natural numbers s greater than or equal to w greater than or equal to 0, we have an SW sphere. Given by the simplicial suspension s minus w smash w smash copies of the multiplicative group. Okay. This is mainly to fix notation. So there are several reasons why one wants to pass to a certain stable situation, and one issue is that the maps in this A1 homotopy category, either pointed or unpointed, they are quite mysterious. And of course there are exceptions. And I would like to give you two examples. One of them was sort of promised as a theorem yesterday, so I should say something. But here's something easy. So you take a smooth scheme over S and you adjoint a disjoint base point in case you don't have a base point already. Yeah? And you may not. And this is suspended simplically n times. And then let's compute the maps to GM. And now if we ask one more thing about our base scheme, then we can actually do this, because if S is reduced, then we can check that maps here can be actually computed by taking maps in spaces. Also, this is pointed. From the same objects up to homotopy. Yeah, the reason is that under this condition, the GM, which on smooth schemes represents the units of the global sections of the structure sheaf, is then A1 invariant. That it's a Nisnevich sheaf it's even an Ital sheaf, so this is not much to worry about. Okay, and now you can check sort of. I didn't specify what type of homotopy. You can use either A1 to parameterize homotopies, or you can take the simplicial interval. It doesn't matter. But if you take the simplicial interval, you can see there's nothing simplicial going on here. This is discrete. So what you get here is that there's just a unique element if n is positive, and if n is 0, what you have here is just what I said. This is the structure sheaf, global sections, and then you take the units. I think the notation that was used was this star, right? But let me write it like this, and it looks like someone's playing tic-tac-toe. Okay, so this we can compute, and there's also another example. So let me abbreviate this this slightly, although this is maybe a bad idea. Okay. So again, we're in the situation, if we impose that S is regular, that we can compute this here easily by computing maps of spaces up to homotopy. The reason is that if S is regular, then Quillen proved that his K-theory pre-sheaf is A1 invariant. And Thomas and Troubaud proved that this K-theory pre-sheaf sends every Nisnevich distinguished square to a homotopy pullback square. So by the unit dilemma, this here is the same as the nth homotopy group of this here, and this is the nth Quillen K group of X. And this is the representability of algebraic K-theory here in the unstable A1 homotopy category. This is so, yeah.
I think you need some assumption for if S is not normal, the GM of X now here above.
Oh.
This might not be a one invariant if X is not normal.
Okay, so
For the second equality, you need S to be normal.
okay.
Otherwise, the unit might not be homotopy now.
Okay.
What? No, it's also for GM. Yeah, I think so. You need some regularity assumptions so
Okay.
GM.
Okay, if I impose also that S is regular, then
Yeah.
I'm fine. Yeah. Okay. Maybe I should have written this as well. So
Okay.
Yeah.
Yes, normal should be enough.
normal should be enough. Okay. Thank you. Yeah, actually, this reminds me. So this representability statement of algebraic K-theory in this form, this works with the Nisnevich gluing, but it won't work with the étale gluing. So this is an instance where we have a condition on the possible Grothendieck topologies we can use. And I mentioned this homotopy purity. And I should also say there is a regularity assumption which also enters in this representability result as stated. And yesterday I mentioned this homotopy purity theorem, which requires the Grothendieck topology to be at least as strong as the Nisnevich topology. So this sort of the freedom you have in forming this motivic homotopy theory, it's apparently not that much. And also for this homotopy purity, smoothness is essential. And this was another thing that one could say maybe a complaint which appeared in yesterday's talks. But for certain statements to be true, these restrictions come up. I know that there are people trying to work around this. Very nice. Yeah, please go on. But if I want to introduce sort of this motivic homotopy theory with the statements that we have, there are these restrictions. Maybe I should not continue with this and rather write something. So these two examples of computations, they were kind of cheating because I imposed conditions so that you can sort of easily compute this. Although you can see here, I mean, this is not easily computed. This is just phrasing. We have these these mysterious homotopy groups, and we can write them in this way. In the case of topological spaces, this is one of the few topological spaces where we know all of the homotopy groups. Okay, so here's something which requires a lot more work. And there are some restrictions again. Let me take F a perfect field. And N an integer which is at least 2. Then Morel computed the morphism sets. Oh, I wanted to abbreviate this, right. Take M plus I, comma I, 2S, N plus J, comma J. And this here is in the pointed A1 homotopy category of this perfect field. Yeah. I don't know about the status regarding finite fields. Maybe it has to be infinite. Okay, this here can be expressed as follows. This is the so-called Milnor-Witt K-theory index. Wait, no, I'm confusing this. Oh, this is very confusing. Sorry. Let's see. So this is in the case M equals N and I positive. And then there's some kind of special case M equals N I B J B N. No, wait. 0, and then we also know that this here is 0 if n is less than n. I should have started with this here. Yeah, maybe that suffices for now. So this here is some connectivity statement, where the connectivity refers here to the sort of the number of simplicial spheres that come up, and this here, is some kind of exceptional case, and this here is the Milnor-Witt K-theory of the field F. Would you like me to give the presentation of Milnor-Witt K-theory at this point? Yes? Okay. So, how do you describe this here? You write down the obvious maps of spheres and write down the obvious relations, and that's it. So what are the obvious maps of spheres that you have if U is a unit in the field? You have a map from the 0 sphere to the 1, 1 sphere, which is GM. It sends the base point to 1 and the non-base point to U. This here we have, and then we have the other obvious map of spheres. So this is a 2, 1 sphere, and this is a 3, 2 sphere. And here we have the canonical morphism, which is the first algebraic Hopf map and usually denoted eta. And then, Okay, this here exists over any base, of course. And the Milnor-Witt K-theory of F is the graded associative ring with unit. It's generated by these elements here in degree 1 and eta in degree -1, and then there are 4 relations. The first one is the Steinberg relation, which you see in Milnor K-theory. This here is 0. Then there's a logarithm. So in Milnor K-theory, the sum of elements sum of units, no, sum of symbols is given by the product. Here there's a slight twist. Eta commutes with the units. And then there's the last condition, which is 2 plus eta times minus 1 times eta is 0. Yeah, so these are the 4 relations. And you can see if you collapse, if you send this here to 0, you can ignore these 2 relations. You can ignore this here, and then you get the usual Milnor K-theory of a field. Okay, what should I do? Yeah, let me mention one more map of this type. So this is due to Azok, Fazel, and there's also some work by Kirsten Wickelgren and then Williams. So you take a field which doesn't have characteristic 2 or 3, and the computation they give is of the following group. You map the 4 0 sphere into the 6 3 sphere, pointed A1 homotopy category over F, and this sits in a short exact sequence where the kernel is some Milnor K group, modulo 24, and the target is some Hermitian K group. I don't know how, maybe let me write this down explicitly without explaining too much. So this is the 4th homotopy group of the fiber you get from sending the K-theory presheaf via the hyperbolic map to the Hermitian K-theory presheaf with respect to the orthogonal group at F. And this is an exact sequence, and let me state that this proves for infinite fields of characteristic not 2 and 3 Suslin's conjecture in degree 5. So Suslin constructed a certain Hurjewicz homomorphism from Quillen K-theory to Milnor K-theory for all infinite fields, and I mean there's a canonical map from Milnor K-theory to Quillen K-theory, and Suslin checked that the composition in degree n is given by multiplication with, I think, some sign and then n minus 1 factorial. So he conjectured that the image here is really just what comes from this composition. So this would be, in this case, 24 times Milnor K-theory. The interesting thing is this conjecture is known in degree 3. This is work by Merkujev and Suslin, and it's related to their sort of treatment of the Milnor conjecture in degree 3. It's open in degree 4, but in 5 it's solved. Yeah? So any ideas on 4? And there's this gap, and someone has to work on it. So all these computations, well, maybe not all. So this computation here, and also this here, and also this here, they are in some sense stable computations. And now I'll get to what this really means. So first of all, we would like to have a triangulated structure on our homotopy category. And in particular, this means that we would like to have a shift functor. The shift functor would be given by suspension with respect to the simplicial circle, so this S1, 0. But for geometric applications, what comes up often are these tome spaces of vector bundles. And if we want to have a strong duality in our stable homotopy theory, we want these tome spaces of vector bundles to be invertible in a suitable sense. And the sort of the basic tome space that you have, so the tome space of the affine line over S. Yeah. So this is, this is A1 modulo A1 minus 0. This is the same as the projective line, and this is to 1 sphere. And we would like to invert smashing with this circle. So I'll give you a quick definition. Let's see, do I need this here? Again, S is a base scheme, Noetherian of finite Krull dimension. It can be generalized if you like, but let's not worry about this here. A motivic spectrum over S consists of a sequence of pointed spaces over S. And structure maps. And the structure maps involve this suspension with the 2-1 sphere. Let me call this, I don't know whether I'll need this sigma. Yeah, so the idea is you want to invert this, so you want to form some kind of co-limit with respect to the suspension, and it turns out in order to have a good categorical properties that this is a reasonable way to go. It's actually not a very reasonable way to go if you want to discuss the smash product. Frederick already mentioned that symmetric spectra are the elegant choice here. So if you like, I can switch right now to motivic symmetric spectra and give you then an associative and commutative smash product. But we can also stick to this and have a handicrafted smash product of motivic spectra, which is, well, only associative and commutative up to homotopy. Okay. So the maps of these motivic spectra are the obvious things. You have a sequence of maps of pointed spaces over S, and you're going to get commutative squares here. And then we get a category of motivic spectra over S. And in order to introduce the homotopy theory, we would have to say what weak equivalences we want to invert. But let me give you a few simple examples of motivic spectra first. So if A is a pointed space over S, then we get a suspension spectrum by taking the following sequence. But specifying the sequence alone is not enough. I have to say what the structure maps are. And the structure maps are identities in this case. And there's a shifted version. If I take a natural number, a shifted suspension spectrum starts with the point up to m minus 1, and then I start with A in at the spot M, and then I continue. Yes?
Why do you say identities? Don't you have to switch two factors to make it just
Basically, you need to shuffle things, no? I mean, because if you smash S2, 1 and S2, 1, it's not necessarily S4, 2, you need to shuffle some S1s.
You don't have to.
I mean, what is S4 2 by your definition?
Oh, this is S21 smash S21. Right?
Okay. Whatever you say. I think previously you wrote some different formula. It was
Oh, yeah, okay. Oh, you're right. I was, yeah, it's still here, right?
Yeah.
Ah, you're right. Structure maps are canonical identifications. Yeah. Canonical isomorphisms. I'm sorry. Yeah, maybe. Yeah. Or should I write it more like this here?
Yeah.
Is this better? Yeah.
You can switch back to the identities.
Yeah. I mean, formally, there's some associativity involved,
Okay.
I guess. Well, no, maybe actually structure maps are identities. Yeah. Okay.
Anyway, S1 and GM.
Pardon?
No, no.
You have to commute if you write, if you replace S21, smash S1 with S4, so you have to compute S1 and GM.
Yeah, then something happens. You are right. Yeah, I was
The
sloppy.
definition of a bispectrum, by definition, we use
Yeah.
this computation.
Yeah.
S1 and GM.
Okay, so let me. Write it like this. Should I say structure maps are identities here as well?
Now it's safe.
Except in one spot. Here. Yeah.
From
Yeah.
nth level.
Yeah. So here's the inclusion of the base point in A. Okay. We have these two examples. I would like to give you a third, more interesting example. And I think there's still time for that. So this smashing with S to 1 has a right adjoint. Yeah. So this is the right adjoint, and it can be considered as the following construction. So this here would by definition be the internal hom from a 2-1 sphere to A. We can identify the 2-1 sphere with a projective line pointed at infinity. And we can identify this here as the fiber of the following map, internal hom from P1 plus to A. So here I have the inclusion of infinity, and here I have hom infinity plus to A. And the internal hom has a sort of obvious formula, and then you can write down this here as the fiber of A, where instead of applying it to a smooth scheme directly, you take product with P1 first, and here you just take it. And this here is induced by infinity. Okay. Why am I stating this? Because Quillen computed the K-theory of projective spaces, and in particular the K-theory of the projective line. And his computation can be rephrased in the case of the projective line as saying there exists a canonical weak equivalence from K to omega to 1 K. And this is section-wise weak equivalence. And this allows us to write down a spectrum which is sometimes denoted BGL, sometimes denoted KGL. So I give you a pointed space in every level, and it's always the same. And the structure maps are adjoint to this weak equivalence here. This is the structure map. Yeah, so tomorrow I'll sort of finish the definition of the stable homotopy category and get representability of algebraic K-theory in the stable homotopy category from this definition here. Sort of, it just falls out. It's immediate. Thank you.
So for K-theory, you are using Killen's K-theory, right?
Yes.
So does it coincide with Thomason's K-theory for regular schemes?
Yes.
With, so even for non-separated?
Oh, I think when I say scheme, I think of a separated pre-scheme.
Okay.
But yeah.
Yeah, okay. Then I know it's coincides.
Okay.
Additional question for me. For the top one, do you need that A to be a fiber class?
Okay, so what at this stage you need a fibrancy for A for it to be true. Yes. But this here is sort of independent of A. So at this stage, yes, I need A to be fibrant in order to have this weak equivalence. So, I mean, what I'm not doing here is replace this by the total right derived. In the case of K-theory, there's not a problem. Yeah, but you're right, I'm sloppy here.
Are there any more questions? So, yes.